Welcome to one of the final talks of this great Fisl organization and conference, the 16th. And I would like to say up front that all of you owe a debt of gratitude to the Software Livre organization of Santa Catarina. Because if they hadn't reminded me that I had this talk here at 3 o'clock today, I would be on the bus, headed out, drinking whiskey. The talk today is called Programming Efficiency for Modern-Day GNU Linux. For those of you who don't know me, you may think of me as a nice old man with a long white beard who goes around giving away free software. Ho, ho, ho. But I've actually started out in 1969 as a programmer, as a university student, a lot of like you are. And I also taught for a small time in a university. And I would take students who had never seen a computer before in their lives, never actually touched a keyboard. Because back in 1970, there were no computers in high schools, no computers at home. And I would take those students and in 2 years teach them how to write operating systems and compilers and other things like that. So I have a technical background. A lot of people don't see that because I normally talk about business and why free software is good for business and good for the society. In 1994, I met Linus Torvalds for the first time, and I saw Linux, and I realized that this was something that was good for industry, good for commercial purposes, good for countries. And at that time, Linux, the kernel, was a very simple kernel. It had no log-based file systems. It was single-threaded. It was single CPU. It wasn't multiple CPU. It was a very simple operating system, and it only ran on 32-bit computers. It was not a 64-bit system. Now, why is that last part important? It's important because if you only have 32 bits in your address space, you can address 4 billion bytes of data at one time. And that may sound like a lot of data when you're just working on the desktop, but it's not a lot of data when you're trying to render a movie, or when you're trying to simulate an airplane, or when you're trying to mine large amounts of data to see patterns for weather. It's very small. But with 64 bits, you could have 4 billion times 4 billion bytes of data. How big is that? That's big enough to fill up a 1 gigabyte disk every second of the day, every day of the year, for the next 5,386 years, and still not run out of address space. It's enough to store 128 bytes of data for every square millimeter on the surface of the Earth, including all the oceans. It's a lot of data. The other thing about Linux at that time is it mostly ran on Intel systems. Systems we call complicated instruction set machines, where every time you execute one machine language instruction, you're actually executing a small program inside of it called microcode. And I decided that it was good that Linux run on different architectures. And because I was working for Digital Equipment Corporation, I got them an Alpha system, which at that point was both 64-bit and the fastest computer system in the world. So I helped him port Linux. I didn't do the coding, I just kind of acted as the band leader to get the coding done to make Linux 64-bit. And then in 1995, I became the executive director of Linux International because we knew that Linux would be good for business, and we wanted to put the rest of the things in place that a commercial operating system needs, such as defending the Linux trademark, making it available for anybody to use it for any legitimate purpose. To create a systems administration certification program that was inexpensive enough that anybody could get certified as a systems administrator, and that you could get the training any way you wanted to, by reading a book, by practicing, by taking courses. It was up to you. And creating something called the Linux Standard Base, which, even though there are multiple distributions, the Linux Standard Base says for any one architecture, the program will work across distributions. This is very important. And then for the last 20 years, I've been going around the world promoting Linux worldwide. That means I've gone to over 100 countries, most of them more than one time. And to Brazil, I've been here more than 50 times. Now, currently, I work in conjunction with two corporations, ARM and Linero. ARM is a company that creates the architecture for a lot of the chips that go into your phones, your home router systems, switches, things like that. They are a very low-power chip. They come in different sizes, 16-bit, 32-bit, 64-bit. And this design is taken by other companies like Broadcom, Samsung, Hitachi, and others, and put into chips and system-on-a-chips, where they might combine a design of ARM's CPU, ARM's GPU, field programmable gate arrays, and other chips. And ARM licenses this design to these companies, and they produce the chips. Unlike Intel, where Intel both designs the chips and produces the chips. Now, there was a problem with all these companies developing their own chips and then wanting to have Linux on them. Each company would hire 50 engineers, and they would create a patch for the Linux kernel to allow their chip to run. And they would send these patches to Linus, and Linus would end up with like 50 different patches from 50 different companies that were all supposed to do the same thing. He didn't know what ones to use. So a friend of mine who had worked on the Alpha Linux port, a person by the name of David Rustling, decided to form an organization called Linero and say to these companies, just give us 2 of your engineers and some money to run the organization. And we will create the one patch that Linus needs to make sure that all of your chips run Linux successfully. So that's who is paying my salary right now. I still do other types of consulting. I've always made my money by doing consulting. My contributions to Linux itself have all been free of charge. So when I go to conferences like this, I am not paid the traditional honorarium of a speaker. They may pay my travel expenses, but that's it. My contributions to Linux are free. Now, this talk is about performance, and over the last 45 years that I've been programming, I keep having these people saying, oh, chips are fast enough, they don't need to be any faster. And I go, what'd you say? That's crazy talk. You know, chips will not be fast enough until I can talk to the computer and it will understand me at least as well as you're understanding me, or at least you're understanding the translator, if there is one. I think there's one. CPUs will never be fast enough. We always want them to be faster. Then another group of people say, Java is the only language we need. And I go, oh, that's more crazy talk. I'll believe that Java is the only language we need when Larry Ellison, the president of Oracle, rewrites the entire Oracle database engine in Java. If it's such a great language, come on, Larry. Rewrite it in Java. You'll never have to port it again. That will happen when the proverbial hell freezes over. Another group of people will say, Nobody needs assembly language. And this one I'll agree with. You don't program in assembly language. I programmed in assembly language for 7 years, but that was in a completely different situation. That was in a computer system that by today's standards was so slow and so small and so miserable that you needed assembly language to get anything out of it. Of course, the same machine used up an area the size of this stage and cost $2.5 million US. So yes, you write some things in assembly language. But today, when systems are running at gigahertz capabilities and multi-cores and multiple chips, to write in assembly language is crazy talk. However, you need to understand what the architecture of the machine is. You need to understand what is happening inside the machine in order to write your high-level language and make it efficient. And that is where the knowledge of 1 or 2 assembly languages is really worthwhile. How can you teach a course in compiler theory if you don't know what assembly language is? How can you teach the design of operating systems if you don't understand the registers inside the machine and the program counter and a stack pointer, which are all part of assembly language? You need to know that. And then, one of my favorite ones, virtual machines make architecture knowledge obsolete. No. Actually, most virtual machines allow the non-privileged instructions to work directly on the hardware and have no abstraction level there. Only privileged instructions and privileged parts of the operating system are in any way emulated and is therefore hiding the architecture of the machine. They may be thinking about an emulator like QEMU, or they may be thinking about a virtual machine like Java, and that hides a little bit of the emulation. But I don't consider Java a real virtual machine. I think of it more as an emulator and a virtual machine. So the other thing about this is, what is performance? Now, I remember when performance was measured in how long does your application run on a particular computer. If your application ran really fast, you say, hey, you have a well-performing application. But I also think about the terms of what type of problem are you trying to solve. Now, how many of you out there like writing games? It's okay, you can raise your hand. I'm not going to sneeze at you or anything like that. How many like writing games? I hate writing games. It's fun. You got all these 3D graphic things. You have sound and music and stuff. It's a challenge. I like it. But see, it's not what excites me in programming. What excites me in programming are really large problems. If you're not talking about at least a petabyte of data, if you're not talking at least 600,000 cores, please don't call me. I'm not interested. Okay? And likewise, I'm also interested in very small problems, embedded systems types of problems. I like those. Those are fun. I'm interested in real-time types of problems. Is your nuclear power plant melting? Do you need to lower the rods to stop it from melting? That excites me. Please don't code that in Java. All of a sudden, your sensor says, nuclear power plant's melting! Java's, oh yeah! Wait a minute, I have to do garbage collection. Garbage collection, garbage collection, garbage. What was I doing? Oh yeah, wait a minute, what happened to the rods? What happened to the city? Oh, no. Don't use Java, don't use Objective-C, don't use C++, don't use any language that does garbage collection. For God's sakes, don't use an interpreter. C, assembly language, or bless its heart, Fortran works fine. Anything where you have control over the machine works fine. One time, I was talking with Linus in the early days of the Linux kernel, and I said, Linus, we'd have a lot more opportunities to use Linux with embedded systems if we had better real-time. And he goes, what's wrong with the real-time? I'm playing Quake, I go to shoot, the monster has a gun in his hand, I go to shoot the monster, and the monster dies, and I'm safe. I said, Linus, put a real gun in that monster's hand and see if you can say the same. And there was silence for about 20 seconds on the other end of the phone. He says, I understand what you're talking about now. And the next version of Linux had much better real time. I think that was version 1.2 if you'd like to try it out. You know, a lot of us carry around these things. Now, this is a different type of performance because what we're worrying about here is not how fast is the application running, because the application was really fast, so you can't get anything wrong. We don't want the application to run fast. We want the application to be efficient. We want our batteries to last a long time. That's how you measure performance in a cell phone application, is how long does your battery last. And it's not just about the batteries of your cell phone. If you're thinking about a server farm like Google or eBay or something like that, then you can think about how many CPUs do we need? Do we really need to buy 10,000 systems, or can we only need 9,000 systems? Do we need to have another Itaipu to power our data center, or can we just get away with 1.5 Itaipus to power our data center? Or maybe we don't have to build any more Itaipus to power our data center. We have a problem with this even today because most people have on their desks this thing called a space heater. It's an electric space heater. We call them computers, but they're really space heaters. And they generate a lot of heat, and they're left on all the time. If we could reduce the amount of electrical power that those space heaters called computers use, then we may not have to build another Itaipu in the future. And there's another thing about performance, and that's the fact that, for the most part, you people use technology that's as old as Alan Turing. The single instruction, single data instruction going along. Some of you have gotten so that you can use a GPU to do single instruction, multiple data, SIMD, we call it. And there's special instructions inside of the Intel instruction set and other processors that handle that now because you've learned how to program it. But there's other types of processing too. There's field programmable gate arrays, where the first thing you do is you tell the circuitry inside of the chip how to configure itself into a processor of some type, and then you pass the data through that processor, maybe in computational speeds 100 times, which you could get out of your single instruction, single data CPU. But most of you don't know how to program that because you're not exposed to it. You don't have those in every single one of your systems. And consequently, you don't know how to write programs for them. And because you don't write programs for them, you have vendors who do not put them into their systems. But what will we use these things for? Well, we could use them for doing really good encryption. 4096-bit encryption. Encrypt everything. The NSA would love that. They spend a month decrypting whatever you had encrypted, and then they would find out it was a lunch menu for your children. They might actually have to go back to asking the court system for the right to decrypt your data, because they wouldn't know whose data to decrypt. We might do something like be able to compress large picture images really good and decompress them really fast, and a whole series of other things which, by the way, also unloads your main CPU from doing that work. And because your CPU could upload these programs to the FPGA very quickly, one FPGA could do a whole series of different things for your systems. Digital signal processing chips are the same. Use them not just to convert audio into digital data, but use them actually as a processor to solve problems. Now, my first language was Fortran, spelled in all capital letters, on an IBM 1130. But my second language was assembler language for this machine, the PDP-8, sitting on the right. And that thing in the front is the ASR 33 teletype, which could input and output characters at the amazing speed of 5 characters per second. Now, there was this urban rumor at one time that the reason why early programmers did not comment their programs is because it took the compiler longer to compile the program, or it took the program longer to run once it was compiled. Well, the first one was true, because back in those days, the data speed was so slow that to read in the comments while you're reading in the source code actually slowed down the compilation. But that was not the reason why. The reason why was you went to print it out. If your program was 3,000 characters long, it took 5 minutes to print it out on the ASR 33 teletype. A lot of you don't even know how long 5 minutes is, but sit there sometime thinking about it. Just sit there waiting for 5 minutes, and you'll see it's a long time. Now, nobody told me that assembly language is different, so I just went, got a book, and learned it. But it's meant a lot in my career, because some of the reason I got my first job right out of university was not all the courses that my professors taught me. It was because I understood what the architecture of the machine was. My job was not to write new programs. My job was to make other people's programs run faster. And as most people will say, in order to write really great code, you need to see how other great programmers work, and you need to know the architecture of the machine and what it's doing. So here's some examples of how I used my knowledge of assembly language in the past. I found errors in the compiler. Now, these days, you don't find too many compiler errors because the huge number of people that are using those compilers, they tend to show up relatively quickly. But back in those days, there was probably only about 1,000 people using any one particular compiler, and we would find problems all the time. And somebody who was writing only in COBOL would come to you and say, I'm looking at my source code for COBOL and I don't see what the problem is. And you look at it and you say, I don't see what the problem is either. It should work. Maybe the compiler is making a mistake. And they go, the compiler? Make a mistake? I say, yes. The compiler is written by a programmer just like you. And just like you, that person came in on a Monday morning, hungover, drunk, tired from Sunday night. Probably had some good sex with their partner. And they realized that the deadline for their code is in just 1 hour. And so they push it through the code system, not checking it properly, and you have a bug in the compiler. And we looked at the assembly language, and sure enough, we could see that it wasn't generating the right code. Now, if he did not, or I did not know assembly language, we could have looked at the source code for that COBOL until the cows came home. If you knew the IBM assembly language, you knew that there were 4 instructions, which were the slowest instructions in the whole computer. One of those was to take a code called EBCDIC for holding numbers and letters. That was a lot like ASCII is today, but EBCDIC was used by IBM. And you first had to convert the EBCDIC number from EBCDIC to something called packed decimal. And then you converted packed decimal into binary. And the instruction to convert EBCDIC to packed decimal and the other instruction, packed decimal to binary, was 2 of the 4 slowest instructions in the machine. The other 2 instructions were to take the binary number and convert it to packed decimal, and the packed decimal number and convert it to EBCDIC. Now you have all 4. Now, why is this terrible? It's terrible because if you left off one little word in your COBOL source code definition of an index into an array, the computer stored it as an EBCDIC number. And so every time you accessed your array, it had to convert EBCDIC to packed decimal to binary, increment the array, add 1 to it, convert binary to packed decimal to EBCDIC. Every single time, millions of times a day, maybe billions of times a day. And all you had to do was leave off that one little word called comp. Easy to do, especially on a Monday morning. I worked in an operating system called Digital Unix, which was one of the best Unix systems in the world. And when we first put it out as a product, it used, you're going to laugh at this, 64 megabytes of memory to run and work in for a server system. 64 megabytes. Not gigabytes, not terabytes, megabytes. And still, my product manager said, it's too much memory. We need to cut it in half. That's impossible. Run a server operating system in 32 megabytes of memory, that's just impossible. But yet the engineers took a year to work on it, and they did it. They made it boot and run efficiently in 32 megabytes of memory. But the really odd part of that was when everybody expected that it was going to run like a dog in 32 megabytes of memory, it actually ran 7% faster. Why? Because in squeezing all of the libraries down, in squeezing all of the utilities down, they got the kernel and the board command shell, command interpreter, and a lot of the X server to stay in the cache of the alpha processor. And therefore the system ran a lot faster than having it expand outside the cache and having the cache misses go on all the time. This is so much so, the utilization of cache is so important that a friend of mine did a PhD study on the use of it. And he did multiplication of 2 large arrays, very large arrays. Remember the problems I like to work on, terabytes at least, petabytes at least. 2 very large arrays multiplied together. Now if you do this like the average high school student will do it using algebra, matrix algebra, you'll know that as you access the elements of the first array, they all tend to stay in the cache of the processor. But as you access the elements of the second array, because in the first array you're going row, 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 in the second array you're going column, column, column. Then every single column is a cache miss. Every single column you go all the way out to the main memory. Now let's use a trick of algebra and invert the second array. So now you're row, 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 row. And then when you get the answer, you invert the answer, you get the same result. That particular pattern goes 40 times faster. 40 times faster. Not 40%, 40 times faster. And all because you understand how the cache of the CPU works. The same type of knowledge allowed me to take a program that ran on a PDP 1170, an old computer with only 64,000 bytes of memory, And by rewriting it, understanding the architecture of the machine, I made it run 220 times faster, from 10.5 hours to 3 minutes. And so this is why knowing the architecture of the machine is so important. Today, a lot of college students are learning Microsoft Office and Oracle instead of how to use your office system to make your business better and databases. They're learning things like Java and information technology instead of assembly language and how operating systems work. And they're using a lot of virtual machines without ever touching the real hardware. And this is creating a problem where students coming out of high school and going into university today know less than the students who came out 20 years ago. Because the students of 20 years ago had to use systems like the Amiga or the Commodore. They had to go out to bulletin boards out on the web, or before the web, out on the internet, and pull down the programs and type them into their basic interpreters. And they learned things like syntax error, and they learned things like array overflow. But today, a lot of these kids get a notebook computer and they never open it up because the notebook computer says you open it up and you void the warranty on your computer. And they buy a game and they put it on there and the game's already pre-compiled. They don't ever see a syntax error. They might see a runtime error, but they can't fix it because they don't have the source code. Then they write a little bit of HTML and they think they're a programmer. So this is why most high school students think of computers like this. The computer is my friend. And we know that's not true. The computer hates you. It knows there's humans out there and it hates them. In fact, at the very best, this is how the computer really works. In fact, it actually looks a lot worse than that. So the real-life effects of this is a dumbing down of the input of the incoming freshmen that the professors at the University of Cambridge in Cambridge, England saw and decided to do something about that. And they created the Raspberry Pi Foundation to create the Raspberry Pi, a computer that specifically was made without a case, that specifically was made without a power supply, that specifically was made small enough to fit in a student's pocket, well, particularly if you wore cargo shorts. And it specifically cost less than $35 so that the students would not have to be afraid of breaking it as they would of breaking a $1,000 or $2,000 desktop gaming system. And of course, there's lots of follow-ons to that. The Banana Pi added more RAM, added SATA controller on it so that you could put disk drive on it, and only cost a few dollars more. It was a dual-core ARM. That was significant because with a single core, if you're working on an operating system, you can't have a single-core computer interrupt itself. That's kind of impossible. But with a dual-core system, you could certainly have the second core interrupt the first one in a critical area. And then, of course, the Raspberry Pi people came back again with another edition of the Raspberry Pi that's now quad-core and more memory. But unfortunately, they still don't have a way of getting data into and out of the system really fast. All they have is 10 100 bit per second Ethernet. That's actually wrong. It's 10 100 megabit per second Ethernet. And it doesn't have a SATA controller. And then, of course, the Banana Pro people came by again, added Wi-Fi to that, and upped it to SATA 2, and so the wars continue. But there's many little computers that are out there, each one of them having a different thing that's interesting from a computer science standpoint. So, for example, the computer in the upper right-hand corner actually has 2 CPU chips on it, one of which has 4 cores, and runs relatively slowly, but uses only a very small amount of electricity. And the one on the other side is also 4-core, but it runs much faster, but uses more electricity. And so when you program this with your operating system, you want the slower, more efficient computer to run your operating system most of the time. But as the load level increases, you turn on the power for the faster processor and start scheduling your processes on that. As those processes die and go away, you can transfer them back to the slower processor. The one down in the lower right-hand corner for my Intel friends is the Galileo, which is a mixture of an Edison chip along with an Arduino. So you can run a real operating system like Linux on there, not Windows, and program the Arduino. And that's a good thing too, because the Arduino is very good for real-time stuff, and that's a good thing. So here's another chip. It's called the Aptiva Parallela. This has a system on a chip that has a 2-core ARM9 processor, but it also has a field programmable gate array. And it has some digital signal processing chips. And I noticed another typo on this. The price of this board is actually $99, not $249. It also has a 16 or 64-core CPU, where each core of the CPU has 32 kilobytes of memory associated only with that core. And people say to me, oh, Maddog, what can you do in 32 kilobytes? Well, we used to have this operating system called CPM, and CPM would only handle 64 kilobytes for the whole operating system and your database and your data, and hundreds of thousands of people used it. So here we have 16 cores that each have 32 kilobytes apiece, and they would be very fast for certain types of problems. And this entire board costs $99 and only uses 5 watts of electrical power. Now, as I said, I work with a company, an organization called Linaro, and they've come out with a specification called the 96 Board Specification. This is for all of their member companies to try and take their system on its chips, fit them onto this board, and that the boards would all have the same mounting holes, would have the connectors in the same place, all use the same type of power connections, and therefore create a standard across ARM boards. There's 2 different editions of the standard. One of them is we call consumer, which is for the hobbyist, you people, for the most part, developers and things like that, and the other is called the enterprise, which is aimed towards server systems and high performance. And the enterprise version would go for about 300 or less than 300 US dollars. The BBC just announced a new little computer system called the Microbit, and their plans are to give away that to every single person in grade 7 throughout the entire United Kingdom, to allow people, their students, to learn what programming computer is all about. I'm going to apologize, I have another 96 board slide in here that I didn't realize was there. So why am I showing you all of this? Because it allows me to do something like this, to build a little supercomputer that fits inside of a briefcase that I could take around to different organizations and show how to do programming across systems. I built this out of 6 banana pies put together. So I have 12 ARM9 cores in that. I have collectively 6 gigabytes of RAM, 6 HDMI ports, so I could have 6 screens up there showing what I want to show. I have 6 SATA ports, which in this particular configuration I'm using to drive 2 1 terabyte drives. I have infrared. I have an 8-port gigabit switch to tie them all together, and the whole thing runs on 70 watts of power. That's a little bit more than a light bulb. So why is this interesting? Because if I put the same operating system on all 6 banana pies, I can program this just like a high-performance Beowulf supercomputer. I can use MPI, I can use different types of libraries to be able to program it just like some of the fastest supercomputers in the world. If I configure it slightly differently, I can show people how to set up a highly available system with a heartbeat going between them and show them how to do failover types of programming, or how to set up a RAID array, or how to set up RAID for striping, or how to set up a distributed file system. I can put this into my briefcase and take it out in a matter of minutes. If I put BSD on some of these systems, I could show them heterogeneous programming between different operating systems. And if I put an Intel processor somewhere in the mix, I can show them heterogeneous with different architectures. I can also show them a 64-bit system running on top as well as 32-bit systems. And all of this, the prototype cost me less than $500 US to build. I'm going through the second round of building this. I hope to get the price down to $400 US. And when I do, I will publish all of the hardware, all of the specifications, all of the mounting holes, and everything else in my blog for Linux Pro Journal, Linux Pro Magazine. So that's kind of interesting. There's another interesting project going on to create what is known as a micro data center. This is for places that don't have access to the internet, do not have access to computational power. In fact, they don't even have electricity. This was sponsored by a number of companies. Invenio, which has done telephony systems for those type of environments before. LeMaker, which is a Chinese company that produces the Banana Pro, and ARM as the CPU architecture designer. So what they wanted to do is have up to 15 of these small ARM computers, up to 10 SSD drives in this data center. They wanted it to run off of 12 volts solar power. They wanted a UPS built into the system in case the solar panel dies for some reason, that the systems keep going long enough to shut down properly. It needed to be passive cooling. That means no fans at all. Now, if you're using SSDs and no fans at all, that means you can have no noise. That means you have a lifetime that could go up to 9 years because there's no moving parts. It also had to operate in 50 degrees Celsius ambient temperature. It had to have a Faraday cage in it so it wouldn't have a lot of noise going out. And it had to run a lamp stack. Now, the hardware for this has been designed. They're going through a contest finale right now to see what group actually has the winning design. Now what we need is the software, and that's where you come in. We want you to design the best software distribution to put on this. What should we be using? Should we be using RAID, using MD at the bottom with LVM as a layer? Should we be using ZFS, GFS, or some type of global distributed file system? Which distribution should we be using? Ubuntu, Debian, Fedora? For distribution makers, here's your chance to shine. Put this on a number of systems going out to places who haven't even seen Windows, and let them know that this is the way that computing should be done. We want it to be very stable. We want it to be easy to maintain because these people may need some help in doing this. And we want it to be scalable and efficient. Now that's one contest that's going on. We have another contest which actually has to do more with efficiency. Over the last 30 years, we've been using an operating system based on a PDP-7 and a PDP-11, machines that had 64K of memory, single CPUs. Now, I used to pay $128,000 for 64K of core memory. but today you could buy a gigabyte of memory for less than $10. CPUs are multi-core, the algorithms have gotten better, and yet we're still using assembly language inside of GNU Linux. There are 1,400 different programs in GNU Linux that have assembly language in them. And these was assembly language that were written for some of these ancient systems. What would happen if we took that assembly language out and let the compiler do its optimization work that it was made to do? They might run a lot faster. They might be a lot more efficient. And so what we need are people to go through and look at these modules and figure out what can we do to make them more efficient. Sometimes you'll figure that, yes, we need to put ARM64 assembly language in there. It's very important. We need to do that. But most of the time, you might be able to test the module and find, let's take all of the assembly language out. We don't need it anymore. The GNU compilers and other compilers, Clang for instance, are efficient enough that it's actually less efficient to have the assembly language in there. We have categories of performance for this contest. It's not all about % speed up. If you can show that you're handling memory better or cache better, or that it's a better algorithm that you're replacing, all of these are categories that you could win in the category of performance. We have several different prizes. You could have a win in, just by porting one application, just by testing one application, you could win an awesome Linero golf shirt, just like the one I have. But you're also entered into a contest to go to a Connect meeting. Linero has these Connect meetings twice a year, usually one in the United States, one in Europe, or one in Asia. And you would receive an all-expense paid trip to a Connect meeting to meet with the engineers, usually 500 engineers coming together with a whole series of expertises. These are some of the best computing engineers in the world coming together to work on putting Linux on ARM processors. And you would win an all-expense paid trip to go there. We have the drawing twice a year. You have many chances to win. But even if you don't win anything, there's some great side effects to this, because you'll learn what assembly language does and how it works, and you'll be able to build a portfolio of the work you've done. So when you go to look for a job and the manager says to you, "What have you done?" you'll be able to say, "Oh, I took this piece of code and made it run 15% faster." Or I took some really scruffy assembly language code and replaced it with well-written, high-level language. And I have these letters from the project team I worked with that said how good my work was and how easy I was to work with. And you can see my code because it's an open source project. And you can see my letters that I put to the email of the project. That is how I got my first job in 1973. It had nothing to do with my degree from Drexel University. You could also do research into new optimization techniques for the compilers. All you compiler writers that are out there, I know you're out there. And maybe even things like automatic detection of race conditions. We're also looking for mentors to help young programmers doing this, college professors and engineers. And what we want to do is gather up examples of this porting work, put it on the website, and examples of performance improvements, and put that on the website so that other people can look at it and see how it works. Perhaps we can develop a university course in performance improvement that could be taught to students around the world. We have a growing list of resources which are available on the website so that people are looking for ideas of how to make the existing code faster and better. And the time frame of this is now. This is an ongoing project. When we finish with the 1,400 modules, we probably will go and open it up for even more performance work to be done to continue making GNU Linux the fastest, best, and most stable operating system in the world. So what should you do right now? Go to performance.linaro.org, read the information about the contest. Up until now, we have asked that you use QEMU and the ARM models to do your porting and testing because we did not have inexpensive 64-bit computers that you could actually buy and put your Debian or Fedora distribution on. But since we do, you may find that that is the easiest way for you to do your testing and porting and things like that. We're also changing the contest prices. So if you do a port, you will get a golf shirt, but you will also get 10 points towards buying one of these or getting one of these. If you do 10 ports, then you'll have 100 points, which probably would get you one of these processors for free. And we're going to have more and more processors as part of the 69 boards programs, both 32 and 64 bits. So with that, if there's any comments or questions, I think I have 1 or 2 minutes left, and you can ask those while I shut down my system. Thank you very much. Unfortunately, I don't have a set of earphones up here, so either you'll have to ask a question in English or somebody would be kind enough to translate it from Portuguese to English. Oh. Somebody says I have, oh yes, I do, someplace. Oop, here it is. I have to turn it on. Electronics always confuse me. Okay, I'm ready. No questions, no comments. I'm getting away easy. Well, you have my email address, so if you have anything that you would like to talk to me about, okay. Thank you very much.